Dear students, good morning. Today we will be discussing material balance with chemical reaction. Material balance with chemical reaction. In chemical industries, chemical engineers carry out unit operations and unit process. What is the difference between unit operation and unit process? Unit operation involves no chemical reaction, simply without any reaction, simply mixing or separation process like that. And unit process, there will be some reaction taking place. So when reaction is taking place, materials will be consumed and materials will be transforming from one form to the other form. Completely they will be converting into the product. In such cases, material balance, how to write the material balances with chemical reactions. For chemical engineers, it is very important to work out any calculations before starting the reactions only. So that is means what feed amounts, what amounts of the feed components they are taking, what amount of the product will be obtained, and what amount will be converting, and what will be the percentage conversion, yield, etc. All these calculations chemical engineers need to work out before starting the operation only. So material balance with chemical reactions, mostly we will be discussing mostly oxidation process. Now just 2-3 problems we will do, and before starting the actual problem we will discuss some basic concepts, some basic calculations, small parts with examples. Then we will solve the actual big problems. So first, material balance means here in previous classes we have discussed material balance without chemical reaction. Now with chemical reaction, that means some reaction, say let it be A plus B gives R. This reaction is taking place. Let the conversion is some 60% like that. Now what are the components that are entering the process? A is entering, B is also entering. Then the product R will be formed. Now in this, the material balance for general material balance we will write first. General material balance. What is the general material balance? Here, input equal to whatever the input that is entering, amount entering to the reactor is equal to accumulation plus disappearance plus output. This is the general material balance equation. This is rate of. Rate of you can include for everything. Rate of input equal to rate of accumulation equal to rate of disappearance equal to and rate of output. Okay. This is the general. But under steady state conditions or under steady state conditions, and also we can say for ideal behavior of the reactors, ideal conditions, then this accumulation equal to 0. Accumulation equal to 0. So our discussion will be ideal behavior of the reactors only. So we don't take this term in our problem. Accumulation is equal to 0. Okay. Then rate of input equal to then disappearance plus output. For example, in this example, consider component A. Okay. Consider component A. For this, what is the balance here? A is entering. So A entering. This is total input. Law of conservation of mass we are writing. A entering is equal to what after entering the reactor, what all can happen to the component A. Okay. After entering this reactor, what all can happen to the reactor? Two things will happen. What is that? Because accumulation is 0 for our discussions. So, two things can happen. One is what? A part of A will be converted into the product. It will be completely converted into the product. And the remaining part, which is unconverted A, will be leaving as it is. So, these are the two things that will happen. So, A converted, that is A disappeared here. A converted, you can say. A converted or disappeared, anything. Converted into product here. Converted to product. Plus A leaving. Plus A leaving. A leaving is what? Unconverted A. Unconverted A. Okay. So, like this we write now. So, A converted and A unconverted. Suppose if conversion is 100%. If conversion is 100%, then this will not be there. Okay. This will not be there. Only whatever A entering, that must be equal to A converting. So, this is the balance. In case of material balance without chemical reaction, this term won't be there. The A will not be converted. Only A will entering will be leaving in different forms. That is material balance without chemical reaction. But with chemical reaction, whatever the A entering, some part will be converted and the remaining part will be leaving as unconverted. If conversion is 100, suppose 60% conversion. Conversion is, if conversion is 60%, then what happens? 60% of A will be converted, the remaining 40% will be, this will be 40% will be leaving. Okay. So, like this we write the material balance when there is a chemical reaction. Because we are going to solve some oxidation process, I will explain here now some small calculations with small example problems. First we will consider, because in oxidation process it is necessary to supply air or pure oxygen. So oxidation reactions, that is reaction with the oxygen. So we need to supply oxygen to the process. So how do they supply? Chemical engineers oxygen to the process. First way is pure oxygen they will supply, or supplying pure oxygen is little bit expensive process, so sometimes they supply air instead of oxygen. So we start with the composition of air. Composition of air. So we know that composition of air is 21% oxygen and 79% nitrogen. Okay, this is by moles. Here all the mole percent. Okay, all the compositions we are going to solve the problems mostly on a mole basis, because here input, total mass input equal to output, that is our material balance, that is mass input, here mass output. Okay, mass output. And or usually in case of solutions, that is while working out problems dealing with liquids, we work out the problems in mass, that is weight and all that. But usually in case of gaseous reaction problems, we will work out in terms of moles. So moles input, total moles input equal to total moles input equal to total moles output. This is our material balance. So mostly for gaseous phase reactions, we will be working out in terms of mole percentages. So now we'll start with the composition of air. That is, air contains 21% oxygen and 79% nitrogen. So we need some quantities like how much oxygen is supplied, how much nitrogen is supplied, and all that. So oxygen supplied, suppose if you want to write oxygen supplied, 21% it is. So air supplied into 0.21. This is all in moles only, mole percentages. So this is one expression, one equation you need to remember. If you know air supplied, and if you want to substitute oxygen supplied, then we calculate like this, air supplied into 0.1. In the same way here, nitrogen supplied equal to air supplied into 0.79. Okay, like this. 79% of air is nitrogen. Therefore, and sometimes we will have oxygen supplied amount, and we need to calculate air supplied. Then how it will be? From the same equation you can write. Therefore, air supplied is equal to oxygen supplied by 0.21, or this is also equal to nitrogen supplied by 0.79. Using this expression, we can calculate air supplied if you know oxygen supplied. Anything, one unknown, the other things will be known. Therefore, from this, sometimes you can also use this equation like nitrogen supplied. It is required in while working out big problems. No, these small things are required. So first only we are writing how these small calculations could be done. So nitrogen, suppose you know oxygen supplied, you know the amount of oxygen supplied. Then you want to calculate nitrogen supplied. Then you can use this one. So this is oxygen supplied into 0.79 by 0.21. Okay, this is another equation. We want nitrogen supplied. So first we take nitrogen percentage, that is fraction, 0.79 by 0.21, that is oxygen. Okay, like this, if you know air, you can calculate nitrogen, or any calculation we can do. Now we will discuss a small calculation. We are going to discuss some new terms, that is theoretical required amounts, theoretical requirement, and actually supplied amount, etc. These things we are going to discuss. So you take a small example here. Calculation of oxygen supplied and nitrogen supplied. Calculation of oxygen supplied and nitrogen supplied when percentage excess over the theoretical theoretically required amount is known. A small, very small calculation. Okay, here calculation of oxygen supplied and nitrogen supplied when percentage excess over the theoretically required amount is known. For that we will consider one example problem. Okay, consider the reaction C plus O2. Consider the reaction C plus half O2 gives CO. We take this equation. CO plus half O2 gives CO2. Okay. This is the reaction we are considering. Now, this reaction, let the oxygen air supplied is air supplied, or we write like this. Air is supplied. Usually you find these things in big problems. Air is supplied in 90% excess over that theoretically required. Theoretically required. Okay. Assume that it is given like this. Air is supplied in 90% excess over that theoretically required. Now you need to calculate oxygen supplied and nitrogen supplied. This is our small example problem. Okay. Consider the reaction. CO plus half O2 gives CO2. Then air is supplied in 90% excess over that theoretically required. The first thing is you need to know is here oxygen is there in the equation, oxidation reaction. So oxygen is appearing in the equation. Any reaction we can see oxygen, but we never write air, isn't it? But practically when we need to supply oxygen, we supply air, because for to run the operation at low cost and all that, simply they will supply air. But if you supply pure oxygen, that is well and good. Okay, purity of the products will be good, and the volume of the reactor required will also be less, because when we supply air, what happens? 21% only is oxygen, 79% is what? Nitrogen. That means unnecessarily we are supplying nitrogen also, where this nitrogen will not be utilized anywhere. That will be simply leaving as it is. So, but many operations they supply air. So, it is given that air is supplied in 90%. Air is supplied in 90% excess. 90% excess over what? That is important. In some problems, many problems we can say. In many problems, they give you like over theoretically required. 90% excess over theoretically. But in some problems, this statement may change. Then depending on this statement, we need to calculate how much air is supplied or how much oxygen is supplied. So here over theoretical requirement, it means that when air is supplied in 90%, it also means that oxygen is also supplied in 90% excess. That is the very first point you need to know. So it is given that air is supplied in 90% excess, means it also means that oxygen is also supplied in 90% excess. Okay, over theoretical requirement. Therefore, in this reaction, first you need to write what amount of oxygen is theoretically required. Then over that 90%, that you need to calculate. So oxygen required, is it let it be question 1. Okay, Oxygen required theoretically. Oxygen required theoretically. This is from 1. From 1. Required theoretically means what? Theoretical requirement is nothing but, I'll write here. Oxygen required theoretically is for 1 mole of CO, 0.5 moles of oxygen. 0.5. Say kilomoles. Then say your basis is 1 kilomole of CO burnt. Okay, you take the basis according to the stoichiometry, then your calculations will be easy. Okay, when you take because 1 mole is appearing here now, you take 1 mole only. If you have 4 moles, you take here 4 moles. Then directly you can pick out the number of moles of other components from the stoichiometric equation. That is why usually try to select the basis which is there in the stoichiometric equation. So this is point. Theoretically required. Theoretically required means what? Theoretically required means required according to the stoichiometric equation. Required according to the stoichiometric equation. Okay, what is mean by theoretically required? Theoretically required is nothing but the amount which is required according to the stoichiometric equation. So according to the stoichiometric equation, for the oxidation of 1 mole of CO, 0.5 moles of 1/2 means 0.5 moles of oxygen is theoretically required. Okay, but now how much is supplied? 90% excess is supplied. So now we will calculate the amount actually supplied. Okay, what does it mean? 90% excess means 90% excess over theoretical means when 100 moles, 100 kilomoles are to be supplied, how much we are supplying? 90% excess means 100 plus 90. 100 plus 90, that is 190 kilomoles we are supplying. That is the meaning of 90% excess. You please understand these terms, percentage excess. Okay, where we need to supply 100 kilomoles, we need to supply 100 plus 90, 190 moles we are supplying. Here in this example, how many moles are to be supplied? Actually required is what? Theoretically required 0.5 only. So 0.5 kilomoles of oxygen is to be supplied, means how much actually we need to supply. So this is 0.5 into 100 plus 90, this one, isn't it? By 100. Okay, like this. That means this is what? 0.5 into 1.9. So simple calculation here. This is 0.95 kilomoles. So this calculation we can formulate like an equation, that is oxygen supplied is equal to oxygen theoretically required into here 100 plus that percentage excess, how much ever it is. Here percentage excess is what? Here percentage excess is 90%. Okay, that is why 100 plus 90. In some other problem, 20% excess. So 100 plus 20 by 100. This from stoichiometry, like that. So this is the important calculation which is required in future problems. That is oxygen supplied equal to oxygen theoretically required. This you can know from stoichiometric equation, and what percentage excess is supplied, that will be mentioned in the problem. So this way you can calculate. So in our example, this is oxygen supplied now. Okay. Next, nitrogen supplied. If you want what? Nitrogen supplied. Nitrogen supplied is what? Oxygen supplied into, which we have written already. Oxygen supplied into nitrogen amount is 0.79, that is 0.21, that is 0.95 into 0.79 by 0.21. So many kilomoles. This much is nitrogen supplied. Okay. This is 3.5738. So many kilomoles nitrogen supplied. Okay. This is how to calculate the supplied amounts. So when we write material balance for nitrogen, no, first we need to calculate nitrogen supplied. Then the same amount will be leaving the reactor because nitrogen is not participating in a reaction. Next, coming to oxygen balance in this oxidation reaction, suppose oxygen balance. Oxygen balance, how to write? We are supplying oxygen, and in that some amount is being, because first of all we are supplying in excess over what is theoretically required. So definitely the entire oxygen will not be using. So some amount will be used up and the remaining amount will be leaving. So oxygen balance is oxygen fed is equal to the total oxygen fed is equal to, or oxygen supplied or fed, whatever it is. Oxygen supplied is equal to oxygen consumed plus oxygen leaving. That excess one and which is not used up and all that, no? Suppose if conversion is 100%, then how much will be leaving? If conversion is 100%, whatever the excess amount we have supplied, that much will be leaving. If conversion is only 60% like that, then excess will be leaving, and out of theoretical requirement also, completely it will not be utilized because conversion is only 60%, only 60% of oxygen will be utilized. So you will have to write then oxygen consumed plus oxygen leaving. This is oxygen balance. So oxygen consumed, or you can say this as oxygen used up. Oxygen used up, any term you can use. So oxygen used up, how to calculate? Oxygen used up is equal to oxygen theoretically required, into fractional conversion. So this is just now what we have discussed, that only, into fractional conversion. Okay. Usually reactions won't be 100%, conversion won't be there. So only 60% conversion. Suppose in the previous example, CO plus half O2 gives what? CO2. Okay. 60% conversion. If it is given like this, 60% conversion. Now, theoretically required, oxygen theoretically required how much in this? for 1 mole basis. 1 mole basis. Oxygen theoretically required is 0.5 kilomoles. But all the 0.5 moles will not be used up because conversion is only 60%. So oxygen used up will become how much now? Oxygen used up will become how much? Actually 0.5 moles are required, but conversion is only 0.60%, that is 60 by 100 into 0.6. So only 0.3 kilomoles. Only 0.3 kilomoles will be used up for this reaction where conversion is 60%. Then, but we are, if you supply 0.5, the rest 0.5 minus 0.3, 0.2 will be leaving as with unused amount, unreacted amount. Okay. So this is into fractional conversion. Fractional percentage conversion will be mentioned in the problem. If percentage conversion is not mentioned in this material balance problems, then you can assume 100% conversion. Okay. So like this is another important equation. Oxygen used up equal to oxygen theoretically required. That means required according to the stoichiometric equation into fractional conversion. If conversion is 100%, this term won't be there. Oxygen used up completely theoretically required. So if conversion, percentage conversion will be given in the problem. Will be given in the problem. Okay. Then oxygen, if conversion is 100%, if conversion is 100%, if conversion is 100%, then this fraction becomes 1. Therefore, oxygen used up is equal to oxygen theoretically required. Okay. If excess is there, then that much excess. Okay. So next, one more point. This is oxygen balance where we have discussed. And another point is product fund. We take the same example. C plus half O2 gives CO2. Same example you take here. Conversion is 60%. Okay. Then what about the product formed? So product formed is equal to actually formed. We can say product actually formed equal to product formed according to product to be formed according to stoichiometric equation. Okay. Product to be formed according, that means when 1 mole is the basis, 1 mole CO is the basis. Okay. For 1 mole, how many moles of CO2 need to be formed? 1 mole only, right? Into here fractional conversion. Fractional conversion. Okay. So this is the equation. That means in this problem, product formed will become what now here? 1 mole has to be formed, but conversion is, fractional conversion is 0.6. So 0.6 kilomoles of CO2 only will be formed in this example. Okay. So product actually formed equal to product formed according to your basis, that according to the stoichiometric equation into fractional conversion. Okay. So these are small calculations, basic calculations we have discussed. Next class we will start the problem. Thank you.